Y'all ready? Yes, no, maybe so. You've stretched your brain already. All right, so just as review, let's move through the levels of particle motion. We have, what is that one? S of t is generally what? Position. And then if I take the derivative of position, I get velocity. And then if I take the derivative of velocity, or the second derivative of position, acceleration. And those are the three main we focus on, but there is another, jerk. Y'all remember jerk? Third derivative of position, second derivative of velocity, first derivative of acceleration, be a jerk. So we've gone forward with it. Now we're going to go backwards with it, is what we're doing. We're going to use integrals to evaluate particle motion, what happens and where we go. So this should be pretty easy today. We'll get a little more in depth as we go, but let's see. Oh, I don't know what that is. Yeah, third dimension of unreality. I don't know. So I can have something to teach later. Okay. What does this mean? There you go. So we do our final minus the position, that initial position, right? To find the total amount displaced. It's not the total distance traveled, but it's how far off I am from the starting point. Does that, y'all remember that? So my little bug could start here, and maybe he goes joop, 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 wherever he goes, but the displacement is, if he ends up here, this is the displacement. Even though he traveled all this way, right? He traveled a lot, but that's the displacement. What about speed? Say it again. That's right. Absolute value of velocity. I think what else I need to tell you? I need to hit on to remember. If I do the integral of speed, what do you think I get? Position. That's exactly right. Position. All right. I think we just do a few. Alrighty. See how much you remember. Let's say would you agree with that? What is that really saying? The derivative of position with respect to time equals velocity as a function of time, right? And let's say I give you an equation for that. Describe the motion of the particle between 0 and 5. Crickets. Tell me what you think. What describes motion? What do I mean by motion? The direction, right, left or right. How can I find that? What tells me the direction? Tell me that first. Sign of velocity? Tells you direction? Okay. How am I going to do that? Plugging in what? I'm going to graph it, I think. Between 0 and 5. I'm going to graph it. Let me graph it and let's see what it looks like. Oh. Yeah, use your calculator. There's a calculator problem. I should have told you that to start with. Sorry. Would have helped you. What, by the way, as you plug this in, what is your initial velocity? Um, here. Put the bottom in parentheses, yeah. -8. That's exactly right. How did you come up with that? Plug in 0. Do y'all need me to show you how I plugged it in? All right, here we go. There's my position function, or my velocity function, I'm sorry. I'm going to do a window from 0 to 5 because that's what it asked me. It just said between 0 and 5. Yeah. Yeah. Tell me when you got it. Yeah, it just followed down to the next line. You can't see it. All right, so let's see what happens. Again, my window, my x is from 0 to 5 because that's all it asked me to analyze. I'm going to graph it. Is that what y'all's look like? Okay, so what happens? So I got an initial velocity of 8, right? And then what happens? The particle's moving which direction? How do you know? It's negative. This is velocity. Remember, this is velocity. If velocity is negative, I'm moving backwards or left. Velocity is positive, I'm moving forwards or right. So this is just saying my little bug is going left, 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 left until I hit this point, right? Let's calculate that point. Say again. 1.25. I didn't mean to push that. So what happens at 1.25 exactly? It stops. That's a stopping. He stops or he rests, right? So he stops, and then he does what? Goes the other way, changes direction, right? So if I'm between 0 and 5, here's what this looks like. Oh, this was 8. Here's 0. Say again. If you put 0 in for t, Oh, sorry. Now, this was 1.25, right? Remember, this is velocity, so velocity is going to tell me what position is doing. Velocity is negative, velocity is positive. So left and right, or I'm decreasing and then increasing on my position graph. Does that make sense? Are y'all remembering that? It's kind of a recap from way back when. All right. Same thing. Same kind of thing. What happens on the graph of position here at 1.25? Speaking graphically, it's a minimum because velocity is decreasing and then increasing. Or, I mean, because the position is decreasing and then increasing. So that'd be a minimum value on position at 1.25. Does that make sense? Do y'all remember? I don't believe all of you. Y'all okay? Is it the test? That's why. See? I didn't want. They're squirrels. What did you? Oh, I thought you said squirrels. All right, let's suppose then, using this same equation, this same information, let's suppose that initial position is 9. What is the particle's position at 1 second? And then what is the particle's position at 5 seconds? Same equation, same information. What the heck am I going to do? Got what? You got to integrate. You're exactly right. Why would they give me an initial position here? Look at you, Adam, so you can find the c, because I got an indefinite integral, right? There's not bounds there. I'm going to have a c. So let's look at what happens. I've got v of t equals, what was my equation? T squared minus 1 over, nope, 8 over. My brain, I have the memory of a gnat, apparently, today. Here we go. I didn't mean to put the dt on there yet. I had myself. So if I want to know position, I'm just going to do the integral of velocity. Agreed? Integrate. Tell me what you get. Mark, set, go. Sorry. Did you already integrate it, Adam? Impressive. I'm telling you. Today? I can't do that in my head. I'm going to have to write it out. Yeah, you can. Is that what y'all got? Well, I had this negative because this, my u, so I had u to the negative second. So whenever I added one here and multiplied in front, it was a negative one, right? So the negative and the negative made it positive. Stop me if I'm wrong. I did it quick on the side. Is that what y'all got? Are you in agreement or disagreement? Sure. What you got too, Adam? All right, so this is position, but this is not the full position equation because I need to solve this C, and now I find out why they gave me an initial position, because I need that C. So my initial position, it said S of 0 is 9, so now I'm just going to plug these values in and say, well, 9 equals 0 plus 8 times 1 plus C, so what is C? 1. And now I have an equation that I can use to find the position at any point in time, ever, and that is 1/3 t cubed plus 8 over t plus 1 plus 1. Yes. I'm just debating on if I should show you this other way to do it. What if I told you, keep the same thing in mind. Before we get to that, because I'm going to do that a second way, I'm going to show you this other thing to think about. Well, you can go ahead and do it. S of 9 would be 1/3 times 5. 1/3 times 125 plus 8 over 6 plus 1. Ugh. So 250 over 6 plus 8 over 6 plus 4/3. Yep. That wasn't, I just cut it in half twice. Okay. What, however, what if I told you, here's where the kind of new stuff comes in. Displacement. Now remember, what does displacement mean? Right? Exactly, the difference in where I started. So what if I told you displacement over time, let's say from A to B, I could find by doing the definite integral from A to B, not a position, of velocity. Could that possibly help you in finding position at a certain time? Yeah, it could, because what I could do, if you think about it, your new position or where you end up, which is what you're looking for whenever you find position, right? If you take where you start, so this is going to be my initial position, and you add your displacement, because if displacement's negative, that means I'm to the left of where I started. And if displacement's positive, I'm to the right of where, right? Are y'all in agreement with me? If I use this concept, then to find any value, I could say then that S of t, or the position, could be, I should say S of B if I start at A, would be from A to B of velocity plus where I started. So instead of having to go through and find that C, I could just use a definite integral and then add back in the initial position. Does that make sense? Y'all are like, what in the world ever? I'm kind of the thought process of using what I already know to do it, but in case there's a multiple choice that looks this way, just so you know, you understand. You don't have to do it this way, but there could be a multiple choice that you know how those multiple choices do, and they might say something that shows something this way, and you need to understand that what it is if you do the definite integral, as long as you add back in that initial, because this is what they're testing is this is displacement. Displacement in terms of velocity and integrals, that's displacement. Yes. I'll even take that same one and show you how it comes out to be the same thing. Same example, right? Because I've already found the integral of it, it'll make it a little bit easier. Let's say I want to do S of, what do we do first? 5, 0, 1, and 5. Let's do 1 first because that's easy. If I do, I'm going to come over here. S of 0. Nope, 1, just kidding. Come on, Stace. So the integral from 0 to 1 of velocity. And what am I adding to it? S of 0, right? Because that's my initial position. That's where I started. So now I'm going to do the definite integral from 0 to 1 of, what was that equation again? T squared minus 8 over t plus 1 squared dt. And then at the end, I'm just going to add that 9 back to it, because that's, so this will be displacement plus initial. Yep. Because that was velocity, because I'm doing the integral, right. So I already know, remember we already said that this was t cubed over 3 plus 8 over t plus 1. I'm going to evaluate that from 0 to 1, and whenever I'm done, I'm going to add 9 to it. A lot of times this is easy because 0 is one of your values if you're going over a time period. But let's see, I got 1/3 plus 8 over 2 minus, now I'm going to plug the 0 in, 0 plus 8. You don't have a C with definite integrals, only with indefinite integrals. Yeah. Let's see, that's 4. So I got 1/3 plus 4 minus 8 plus 9. One-third plus 3. -4, nope, 5. Is that what we got the first time? 2 ways of doing the same thing. So this is where I plugged in 1, and this is where I plugged in 0 and subtracted. Yes. So this may come in handy because if you're already asked, like on your homework, you're going to be asked to find the displacement and then asked to find the particle's final position. Well, if you've already found displacement, why go through and do everything else? Just do displacement plus initial condition, right? Our initial starting point. Does that make sense? I feel like no. But let's do the other one. We'll do the other one. Somebody said the second one. What was that? S of 5? So S of 5. So I'm going to do displacement from 0 to 5. And then I'm going to add in that 9, which was that initial condition. It's 0 for your time, yes. So it's always, initial position is always s of 0. Initial velocity is always v of 0. Initial acceleration, a of 0. It's when you plug 0 in for time, because that's where you start, right? When time is 0. Again, I'm going to use the same equation, plus 8 over t plus 1 from 0 to 5. 125 over 3 plus 8 over 6 minus 0 plus 8. Whoa, I messed up somewhere. No? Oh, you're right. Say again. That's where, so this is where I plugged in, golly, it's not working with me. This is where I plugged in 5. This is where I plugged in 0 and subtracted the 2. Let's do one together from your homework. So you see exactly what it is. And, yeah. These are all non-calculator, by the way, which is fun. The ones in your homework are non-calculator. I think this one would be a non-calculator. You think this one would be calculator? I think initially it was calculator to find that 0. What is happening? I don't either. I don't even know what's going on. Do y'all need a break? You need a brain break? Gray is calculator or non-calculator? Non, right? Y'all want to do the calculator together or the non-calculator together? Let's do number 6 then. Non. The function v of t is the velocity in meters per second. This time they give us units, so be very cautious of that. Use analytic methods to do each of the following. First part, we're going to find when the particle is moving to the right, when it's moving to the left, and when it's stopped. Then we're going to find the displacement and the final position, given that s of 0 equals 3. All right, so let's just start. Let's dig in. Part A says, when is the particle moving to the right? When is it moving to the left? And when is it stopped? So how do I tell about direction? Sign analysis of velocity, right? That's going to tell me what the position function is doing. So I'm going to set it equal to 0. And I'm only between 0 and 4, right? Say right, because that's right. Okay, thank you. So and if you think about what a square root graph looks like, this will make sense to you, right? I'm flipped upside down because of the negative t. So I'm just kind of doing this. So I shouldn't have, we'll see what happens though. We'll see what happens. Square both sides, I get 0 equals 4 minus t. Is that right? Okay. I'm only from 0 to 4. So when I'm go left, so plug something in, maybe a 1. Am I positive or negative? But this one's kind of special because what happens at 4? Stops, right? How do I know it stops? I know it stops because velocity is 0 at 4, right? That tells me it stops. So as I describe this, I'm moving, did it say left or right? When is it moving left? When is it moving right? And when is it stopped? So the particle moves right from 0 to 4 seconds. Stops at 4 seconds. And I probably should include because velocity is positive. And it stops at 4 seconds because velocity is 0 here, or v of 4 is 0. Tells me that it stops, right? Any questions about that part? That's kind of old. That goes back to what we were doing before. Now the next part says, find the particle's displacement for the given time interval. That's the first part. And then it says S of 3, or S of 0 is 3. What's the particle's final position? So the first thing is just the displacement. How do I find displacement? That's right. I could go in, I could integrate, find the C and solve since I have an initial position, but since they asked me just for the displacement to start with, and I'm going to have to do that anyway, I might as well just do displacement from, what did it say, 0 to 4? And then, we'll answer the last part in a minute. All right, so V of t square root of 4 minus t. Mark, set, integrate. This isn't my favorite part of the chapter, by the way. I told y'all this was my favorite chapter, and it is. But when we get to our areas between curves and revolutions and all the fun stuff, it's going to be great fun. Great, great fun. No, right. We're going to use that in just a minute. Add. That's to find the final position. It comes out to be this in the end. If you adjust your bounds and then you could, but what if that was, I'm just in the habit of doing it because what if this was minus 3t? It's not. It's not, but it is negative. So you'd have that -1, right? Yes, because that's what I said. This one comes out to be the same thing. You could have, yeah, right. Well, it's a good habit to be in to check because if there's a coefficient in front of t or things start happening that you understand, you see what I did because my du was -1, right? So I gave it the negative inside and out, but whenever I did that, I adjusted my bounds to account for the u. U was 4 minus t. But then my bounds were switched, so I switched them and negated. Okay, so because my smallest number wasn't on the bottom, here, because u was 4 minus t. Sorry. Oh, I got it backwards. That'd be 3/2, so that's 2/3, 3/2 from 0 to 4. I don't have to go back and plug in that 4 minus t because I adjusted my bounds. Does that make sense? Remember, you can adjust the bounds in the beginning, or you can plug your u back in the end. Either way is okay, but you have to adjust one of the two. That's where I did this. Because they were still in terms of t and not u. Then whenever you should did you get 8/3? What'd you get? Wait, this is 4 to the 3/2. Sorry. This would be 2 to the 3rd is 8. What did you get? 16/3. Yes. No? Okay, so if you stayed here and you said, well, this is t, what did you say, 4 minus t? You're going from 0 to 4. So what did you say the integral of that was? Or what's the antiderivative of this? 2/3. Okay, so now wait just a second. Let's check it, right? If I go back and check it and do the derivative of this to see if I go back to what I started with. I multiply through, right? And I get 3/2 times 2/3, 4 minus t to the 1/2, and now I got to chain it times -1, right? See where that negative is going to, that's why you have to be really, really, really careful. So the derivative of this would be negative 4 minus t to the 1/2 and not 4 minus t to the 1/2. That's how I know I messed up. That's why your sign's different. Does that make sense? That's why all of this was important in the beginning where I switched them around and flipped the sign. I know, I'm sorry. Don't let these simple little things trip you up, though. Listen, I still come over to the side and write this out because I need to visually see it. I have to visually see it to make myself understand. And then I either have to adjust the bounds here, or once I plug in, then I need to plug my 4 minus t back in for u here before I evaluate. One of the two has to happen. Adjusting my bounds is plugging in, taking this u equation and changing these to be in terms of t. So 4 minus 4 and 4 minus 0. The reason I flipped them around was because whenever I did that, I ended up with 4 and 0, and I need the smallest one always on the bottom. So I did this. So I did two types of adjustment for this one, which in the end wasn't a huge deal for this one, but it did change the sign of your answer, if that makes sense. Yeah. Now, that's displacement. That was the first part of the question. Second part of the question says, what's the total distance traveled by the particle? Or actually, no, I lied. There's three parts. I didn't see part C. What's the particle's final position? What did we solve for? What was that find? That was displacement. This is displacement. And what did it say? Meters. So final position, you're exactly right. I just add. What was that initial position? Now, yes, in the beginning of the problem. Now I want you to think about this. This one you have to think about a little bit. Total distance traveled. How does distance, okay, so yes, it's velocity. It has to do with velocity. But if I just do, remember the integral of velocity on this definite integral, that's displacement, right? That's not total distance traveled. How could I find total distance traveled? You're exactly right. There you go. There you go. You do, but what do I have to do here? I need total area, right? Total area would tell me total distance traveled because it doesn't matter if he's moving left or right, he's still moving. And I want to know how much he moved all together. So what did you learn way back when always describes, or you can use to describe distance because it's always positive? Speed, or, which is the same thing as the absolute value of velocity. So that's what I'm going to do. So the difference here from here to here of the absolute value of velocity, yeah. Well, and this is going to be I'm surprised they put this non-calculator. I guess because it's such an easy function. Because it's always right, right. Say again. Star this or highlight this somewhere in your notes because that's big. Say that one more time, Alex. I'm sorry. Yes, but here's the difference. Here, think about if I've got this. Let me do it just first quadrant. Something like this. If this was velocity, right, and I wanted to know the position at this time right here, or I wanted to know the total distance traveled, right? If I did the integral, it's taking this area and this area. Well, displacement would be if I added this plus this, but this one's negative, right? Total distance traveled is this, that's exactly right, plus this, but I need to do the absolute value. I need to make sure that this stays positive. It would flip it up here to give me this value. Does that make sense? Because I need it to be positive. Okay. So if you think about it, though, Abby made a good point with this one because we know this was the square root of, what was it, 4 minus t. And if you know what the square root graph looks like, well, and actually we already did the sign analysis from 0 to 4. That's not telling me the... So if the velocity is always positive, then the absolute value of that is the same. So in this case, since it's always positive, this equals this when I'm from 0 to 4. Does that make sense? Why? If it cut off, if I had a cut off here and said from here and this was negative, then I need to find this integral and I need to change the sign here to make it, to find, does that make sense? To find the absolute value. Okay, that went not as well as anticipated. So it's got, if think about, do you understand the sign analysis that we do? Velocity, position. If it's always positive, it never goes negative. But let's say at 2, let's say I was positive and then negative, for example. Okay. Then what I'd need to do is I'd do the integral from 0 to 2 of velocity. And then I'm going to do the integral from 2 to 5 of velocity. But for this negative piece, instead of adding, I'm going to subtract. Because what happens is this is going to give me a negative value. And I can't have it be negative. So I'm going to force the sign over to positive, which is the same thing as doing the absolute value of velocity. So you'd have to split it into multiple integrals is what I'm getting at.